So today we are very happy to have all of you here at the center. And we have Bernard Teissier, who is coming from CNRS Paris. And he will be talking about a geometric introduction to valuation theory via infinite dimensional algebraic geometry. Professor?
Thank you very much. I'm very happy to be here. It's my first visit to this center. And I thought of making an introduction with a little history. So my first title was Why Valuations? It's interesting that valuation theory has two main sources at the end of the 19th century, the beginning of the 20th century. The first one is Dedekind and Weber, and the second one is Hensel. Although Hensel was no real stranger to what Dedekind and Weber did, but with different viewpoints. So what did Dedekind and Weber do? Well, Dedekind had put on a very firm basis the algebraic theory of numbers. This means taking a finite extension of the field of rationals and taking in that extension the integral closure of the ring of integers and looking at the algebra of that ring. And that played a very important role. It was inspired by ideas from Kummer and Kronecker and so on, and it was really the basis of modern algebraic number theory. On the other hand, one of the most successful ideas of the 19th century was the idea of Riemann surface. But the Riemann surface was completely in the complex analytic world. And Dedekind and Weber wanted to put it on an algebraic basis. So the problem is like this. You work over the field of complex numbers. You take an irreducible polynomial in two variables. And now you may want to look at it as an algebraic extension of the ring. Well, for the moment, I'm with rings. So let's stay this way for the moment. This is, as we know, the ring of algebraic functions on some algebraic curves in the algebraic curve in the plane. And the goal of Dedekind and Weber was to construct algebraically from this algebra the Riemann surface and to define the genus, because the genus was defined topologically. And they wanted an algebraic definition of the genus and, if possible, an algebraic proof of the Riemann-Roch theorem and all these things which go with it. So I didn't write the things quite correctly, because from their viewpoint it was more like the field of rational functions in one variable and then an extension of this field and then we can take f as y to the n plus a1 of x, y to the n minus 1 plus a n of x with a I of x in c of x. So, and they had a very beautiful idea, indeed. You have this algebra, and you want to make a Riemann surface. So you need to define a point. And the beautiful idea they had was to view a point of the Riemann surface as a place where you evaluate functions. So a point is something that gives a value to a function. To us today, it's completely natural. It's almost obvious. But at that time, I don't think it was obvious at all. So if you take a non-singular point, and you take, so let's call the curve C, and on C I'm going to look at the field of rational functions, which is the fraction field of this guy. In fact, in this case, if f is irreducible, this is already a field. So this is a field. You can think of its element as the restrictions to the curve of rational functions. And a rational function like that, what does it do to a point? It gives it a value. But this value, of course, may be infinite if the point happens to make the denominator vanish. So they gave this definition of a place. A place on this field is a map from the field to another field union infinity. But it means it gives the value infinity to some elements, to some of those ratios. And the condition is that the set of elements, say, let's say G over H. If G over H, let's say P for the place, if P of G over H is infinite, then P of H over G is finite. Is in L, that means. Okay? And even it has to be 0, because if you look at G over H, if H vanishes, it means that H over G is vanishes. In fact, vanishes. Why do you want to take a larger field L? Because your curve may be defined over C, or it may be defined over a smaller field, in fact, over the field of algebraic numbers, for example, and you may want to take values at points which are not in the base field. Suppose that K, instead of being the complex numbers, is the field of algebraic numbers, Q bar, then you may still want to evaluate your functions on at a complex point. So you must think of taking values in a larger field. Okay, so this is the definition of a place. And then they realized that works perfectly well as long as you look not only at non-singular points of the curve C. But if you have a singular point, even the simplest kind of singular point, a rational function, the value that you will compute for your rational function depends on the branch along which you tend to the point. So a singular point like this will give you two places. Okay? On the other hand, if your curve is an affine curve, as I implied, you may also get places by looking at the branches which go to infinity and looking at the limit values of, say, G of xi over H of xi, as xi tend to infinity along some branch, some asymptotic branch, the limit of this will give you a place. The limit value of this, it may be infinite, it may be 0, it may be whatever, but it will give you, again, a place. So the beautiful thing is that you realize that if you look at all the places of the field K of C, I look at places which are trivial over the base field. That means we assume that they send the base field to itself. L is an extension of the base field. The set of places of K of C is, in fact, in bijection with the points of the normalization of the projective completion of C. That means the set of places, it does two things at once. It adds points at infinity, which we did not see because we were in the affine plane, and it separates the branches which need to be separated. So in fact, it normalizes, as we say nowadays. It resolves the singularities. So starting from there, that's what they did. And they continued, they defined the value of a differential, and they defined a genus, and they could prove the Riemann-Roth theorem. If you want a very nice exposition of this theory, in a more or less modern style, there is the book of Chevalet on algebraic functions of one variable, which does the theory of Dedekind-Weber in much more detail, and also over an arbitrary field, which may be of positive characteristic. Okay, so we look at this, it looks very innocuous, but let us look for a minute at a subring, R nu, I will call it R nu, of some field, in this case K of C, which has the property that if an element of K of C is not in R nu, then x minus 1 is in R nu, and in fact, I will look at local rings. I will assume that this guy has a unique maximal ideal, then x minus 1 is in M nu. You think of this as a field. So you can think of x as A over B. And this means that if B does not divide A, then A divides B. It means that if you look at the ideal generated by A and B in R nu, it has to be generated by one of the two. Okay? So definition, a ring R nu, which is an integral domain. Such that whenever I have A and B in it, non-zero, then either A divides B or B divides A, that's called a valuation ring. So you see that, in fact, the concept of a place is extremely close to the concept of a valuation ring. And in fact, given a place, the set of elements in K of C which have finite value is a valuation ring. And conversely, if I have a valuation ring in a field, then I can look at the map from K of C to R nu modulo the maximal ideal, which is a field, union infinity, which sends the elements of R nu to their class modulo the maximal ideal and all the others to infinity. And that is a place. So places are in bijection with valuation rings, and we're going to be interested mostly in valuation rings. But when you have defined that, in fact, you realize that you have defined much more than the idea that a function may become finite or infinite at some point. Because this condition, which I've written here, that A, B is either A R nu or B R nu, allows you to define an order, a pre-order, so that A is less than B if B over A is in R nu. And the important thing is that this is a total pre-order by definition. Any two elements are comparable. Now,
I don't know what pre-order means.
Pre-order means A less than B and B less than A does not necessarily imply A equals B. Okay? It's transitive, but it is not. Okay.
You don't need Euclidean.
No. Good remark. If this guy happens to be Noetherian, then this implies immediately that every finitely generated ideal is generated by one of its elements, or one of its generators. So if R is Noetherian and local, this implies that R is local, by the way, this condition. It's an exercise. There's either A divides B or B divides A plus integral domain. It implies that it's a local ring. So to continue with Tony's question, if R nu is Noetherian, then the maximal ideal has to be principal. So the only Noetherian valuation rings are local rings whose maximal ideal is principal. These are regular one-dimensional local rings. And, so all the valuation rings that we meet when we do valuation theory are non-Noetherian. That's why my lectures contain infinite dimensional geometry, because we are going to deal with non-Noetherian ring most of the time. Okay, so this is a total preorder. Now we can define an equivalence relation that A is equivalent to B if A is a unit times B, where U is invertible in R. This equivalence relation is compatible with the product, obviously, the product in R nu. And so if I look at R nu modulo this equivalence relation, then it is a certain set which has now a total order. And on this set, multiplication gives a semigroup structure. So this is a formal way of saying that not only do we have the idea that a rational function vanishes or becomes infinite, but this tells us that this function vanishes more than that function. That's the idea. Its order of vanishing is higher. So the notion of valuation contains the idea that you vanish along something more than somebody else. And this is capital. So it has a semigroup structure. You can symmetrize it. First of all, you can symmetrize it to get a totally ordered abelian group. Because I started from R nu, and now I have a map from the fraction field of R nu, which was my K of C. Let's call it capital K for a minute. So I have a map from this minus 0 to phi. You have a semigroup, you take minus formally, you get a group. Some people write this, well, anyway, okay? It's clear. Okay, and this map satisfies two conditions which follow immediately from the definitions. The first condition is that nu of AB is nu of A plus nu of B. This statement contains no mathematics. It just means that we are writing the multiplicative law of our ring as an additive law in our abelian group, but it contains no mathematics. The one which contains mathematics is that nu of A plus B is greater than or equal the minimum of nu of A and nu of B. Many things I will assert and not prove because I don't have much time, and if I don't prove them, I will tell you if it's difficult. But this is not difficult. Okay, so this is something you see almost immediately, like the fact that this condition implies that R nu is local. You just look for it and you find it in 2 minutes. Okay? So we have defined a valuation ring. We have defined evaluation on a field. This is completely general statement. Evaluation on a field is a map from K star to a totally ordered abelian group, which satisfies these two axioms, these two conditions. So now, what do we do with that? Well, first of all, we want to understand a little bit. At this point, I stop and I tell you a few words about Hensel, because it's interesting to compare the two. The motivation of Hensel was different. He was not trying to understand Riemann surfaces from an algebraic viewpoint. He was trying to solve Diophantine equations. And we all know that it's difficult to solve Diophantine equations. But Hensel's method was to try to solve. So this, imagine that f is a polynomial with coefficients in z and some variables. Okay. Then Hensel's method was to think maybe it's easier to try to solve congruences like that. Like you look for integers modulo some power of a prime, and you want the function to be 0 modulo some power of a prime. And I don't know how he got this idea, because I don't think he ever really wrote that. But his idea was to use Newton's approximation method. Newton's approximation method tells you when you have an equation, you can find zeros by a very clever method involving dividing by the derivative, taking a point more or less at random, and then initiating an approximation process using the polynomial. So Hensel's idea was to use this. The problem is that Newton's method works on the reals, but here we are in a different world. We are in the world of integers modulo p to the n. So he had this idea of defining a norm on the integers, like this, on the rationals, in fact, like this. When you have any rational, you can write it a over b, where a and b are integers, which are coprime. These are not the same a, b than there, okay? These are coprime integers. And then I can, given a prime p, I can write this in a unique way. P to the s a1 over b1 with s some power of p, which may be negative, and a1 and b1 prime to p. Then the norm defined by Hensel is p to the minus s. So the idea is that if you have a large power of p, then the number is small in this norm. Okay? And but in doing so, he defined evaluation, because the s which you see here, it's evaluation on the field q, so q minus 0 goes to the integers. And if you check, you see that this s actually defines evaluation on the rationals. Okay? So the norm of Hensel is just p to the minus the p-adic, what we call the p-adic valuation of x. Any question? No. Okay? So you do that for every p. And So Hensel's idea was, if I want to have solutions, first I complete Q with respect to this norm, like people knew how to do that in various vector spaces at the time, so complete Q. For this norm. Then, if you are lucky, you can use Newton's algorithm, which now we call the Newton-Hensel algorithm, to find solutions of the equation. And then you see whether those solutions exist as rationals or not. Or if you have something called Hasse's principle, that in some cases, if you have a solution for every p, then you know that you have a real solution. This is very rare, in fact, but it works sometimes. Okay? So this was Hensel's introduction of valuation, and in fact the two worlds did not communicate very much over the ages. This Hensel's work produced an enormous quantity of work in number theory and in logic, because the model theory of valued fields was a very active field of research since, I don't know, at least since the 50s, probably before. But these two worlds did not communicate too well. And as I hope to convince you that they should more, in any case. All right. So, of course, this was generalized. This is for the integers. You can, of course, generalize to extensions of the field of rationals. This is, again, a whole beautiful theory, which has many, many ramifications. And in fact, if you follow this through, today you arrive to Berkovich geometry. If you follow the path, this idea leads to Berkovich geometry nowadays. And the relationship between Berkovich geometry and the theory of valuations is still in the making. It's a field which is developing, and which is still in the making. So let me go back to curves for a little while. And give you a little idea of what I want to do in the sequel. Oh yes, I should say that without exaggerating too much, you could say that the people at the time of Dedekind and Weber and Hensel, and especially Dedekind and Weber, because they make it very clear in their paper that they are inspired by the work of Kummer and Kronecker on algebraic number theory, and they don't mention the work of Dedekind himself, which was actually absolutely crucial. But the parallel between looking at, when you take Hensel's viewpoint, what actually you are doing is you are looking at an integer as a function on spec z, which vanishes at certain primes with a certain order. And when you look at the affine line, and there is a theorem, yes, I want to make the parallel because there is the theorem of Ostrovsky, which says that the only absolute values on the rationals are the p-adic and the usual one, which we write x infinity. And there is a similar theorem for the affine line, which is absolutely parallel, which says that the only valuations which are trivial over the base field, that means they give value 0 to every element of the field, except 0, which goes to infinity, are those which correspond to the ideal x minus a. So they are the corresponding valuation ring are k of x localized at x minus a for a in an element in K. All these are valuation rings. It's very easy to verify. And the degree of a polynomial gives you a valuation. You may have to put a minus sign in front of it, but because the degree is also an order of vanishing, it's an order of pole. The degree of a polynomial is the value of the order of the pole that it has at infinity. And the two theorems are absolutely parallel. And don't think that the people at the time did not know that. They don't write it explicitly, but they were very well aware of this correspondence between the integers and the affine line. At least the impression I get by reading the literature. Okay, so let me go a little bit more into the algebraic case, saying suppose that we have a singular point, and what relationship does it give to evaluation? So to simplify things, let me take something formal. I don't really need that, so let me not. No, I need it. Yeah, it's to give you an idea, anyway. So I'm looking at a curve. So I'm in the situation of trying to understand a Riemann surface, but I'm looking at a particular singular point, which I call the origin. And because I want to avoid certain problems, I look at formal power series instead of polynomials. In this case, assuming that K is algebraically closed, this ring is contained in a unique valuation ring, which is the ring of power series in one variable, T. So this is obviously a valuation ring. If you look at the definition, two series, whether one divides the other, is decided by the order in T. But now, so the value group of this valuation, have I defined that? No. Yes, there. The value group is Z. And I want to stress, because it's going to be important in the sequel, the semigroup of values of the T-adic valuation on this subring. If you look at the values, so every series has an order in T. It's the smallest exponent which appears in the series. So, and this is evaluation with values in Z. In fact, in KT, the values are in N, in the integers. Now, I restrict this valuation to this subring. Because it is a subring, the elements multiply, so the valuations add. So this is a subset of, let us say, of the integers in this case, because there are positive exponents here, which is a semigroup. 0 is in there because the constant has order 0. So gamma is a semigroup. And the thing that I want to stress for the sequel is that this semigroup contains a lot of information on the singularity which F may have. In fact, it contains all the information you need to resolve the singularities of the curve. It gives you the algorithm for resolving the singularities. And this is a very important fact. And while I'm at it, who does not know about Puiseux exponents? Who does not know? Okay. Thank you. So when you have a curve like that, there is a theorem of Newton, which I won't prove, which says that still in characteristic 0, you can parameterize this curve by something like that. Let me put exponents like that. So I want to explain by words because it's too long to write. First, when you can parameterize by x equals t to the n and y a series in t. Parameterization, it's clear what it means. It means a map from, let's say, the complex disk to my curve C. It means that f of this parameterization, xt, yt, this is identically 0. So my curve is described by this parameterization as well as by the equation. Now, the exponents have certain arithmetic properties. And I write y. At first, I don't know anything about it. So I can always, by a change of variable, assume that the first exponent here is at least equal to n. Because if it is smaller, I invert the roles of x and y. And then the first exponent may be a multiple of n, the next one 2, and so on. But at some point, it has to stop. Because otherwise, my curve would be y minus x something minus x something, and it would be non-singular. So at some point, I must get an exponent which is not divisible by n. I call it beta 1. Then I look at the greatest common divisor of n and beta 1. And then I look at the next exponents, the next terms in the series, whose exponent is divisible by E1. if it stops, then I stop. If it does not, I get to an exponent beta 2, which is not divisible by E1. So I surround it like that, and I look at the greatest common divisor of E1 and beta 2. I call it E2. And every time it decreases strictly, so after finitely many steps, this has to stop. And then I have isolated a number of exponents, n, beta 1, beta 2, and so on, and beta g, and this is called the characteristic exponents of the curve. And they describe its topology, the local topology of the curve inside a little ball or a disk in the complex plane. Okay, so in characteristic 0, it's well known since the Italian geometers that there is a very close connection between these numbers, the Puiseux exponents. They're called the Puiseux exponents because it's actually Puiseux who pointed out their importance. And between that and the resolution and the semigroup. And in characteristic P, this fails completely. For example, in characteristic 0, the semigroup here, like all numerical semigroup, it's finitely generated. So it has a number of generators, which are integers. If I'm going too fast, stop me. If you have a semigroup of integers, it's a theorem, which is not difficult to prove, that it has to be finitely generated as a semigroup. That means there are finitely many integers, such that your semigroup consists of taking sums with positive, non-negative coefficients of those. And in characteristic 0, the G here and the G here are the same. And there is a very simple relationship, which I won't write because we won't use it, between the generators of the semigroup and the Puiseux exponents. And one of the things that will come up tomorrow, I think, or maybe today later, is that in positive characteristic, this thing breaks down completely. And that is one of the reasons why I think one should avoid all the ideas coming from Puiseux in trying to understand resolution in positive characteristic. So this was more or less an aside.
So I have a question.
Yes?
You know Lay's carousel of the
Yes.
thermometer?
Yes, yes, yes.
And it's there's these speed zones based on the can you see that thermometer action in all the carousel reevaluation?
Through the semigroup?
Yeah.
No. Well,
Maybe an automorphic
no.
look of speed?
Oh, no. There is what you said touches a deep question to which I will come back.
I didn't mean to ask a deep question.
No, but it's not because the carousel actually has to do with the certain discriminant, and this certain discriminant, part of its carousel depends on the Puiseux exponent, and because there is this relation with the semigroup, we can always say that it depends on the semigroup, but the geometry of the relation is much more delicate. Okay, so now I've told you, I think, very roughly what valuations do in dimension 1. Dimension 1 meaning for curves, building the Riemann surface, and for the integers, let us say, or extensions of the field of rationals. Now, I must convince you that in dimension 2, the situation becomes dramatically different. And it will become also dramatically different when we go beyond dimension 2. But first, in order that you get an idea of what kind of zoo we have to deal with, I would like to tell you a few things about the valuations. So what I do is I take the affine plane, the ring of polynomials localized at the origin, view this as a subring of the ring of rational functions on the affine plane, and I'm trying to understand which valuation rings are new of this ring. Because there is a base field, it always means that the intersection of the maximal ideal of R nu with the base field is 0, which means that the valuation is trivial on the base field. It gives the 0 value to every element of the base field except 0, which goes to infinity. So in this case, infinity. Okay. So, so I want to understand which valuation rings contain this. So let me begin by giving you some examples of valuations. The first example, nice and simple. You look at the order. You have a polynomial P of xy. It starts with a homogeneous polynomial of a certain order. You look at the Taylor expansion. And you check that the map which to P associates M, that is evaluation with values in Z, of course. Well, the value group is Z. This one has values in the integers, of course. So that's not so exciting, but still. Then, which order did I put these examples? Oh, yes. Then the next simple case is to say that I give to x and y weights. So I give to x a certain weight, which are real numbers and positive. And then to a polynomial P of x and y, I attach the minimum weight of its terms. Okay? Is it clear? You look at every term, it's a coefficient times the monomial in x and y. You calculate the weight of this term, and then you take the minimum, because you have only finitely many possibilities, it exists, and it's easy to see that this is evaluation. When you multiply, these things add, and when you take the sum, you have this the inequality. So these are called monomial valuations. Then, for example, here you can take w of x equals 1 and w of y equals tau, which is an element, a real number, but which is not rational. This will imply that it's impossible for two monomials to have the same weight. So there is only one monomial which gives the minimum. In this case, it's very nice, because you always have, when you add, you can compute very easily the valuation. What is the value group? The value group is, of course, z plus tau z. Take a monomial, you have a certain number of integers and multiples of tau as a subgroup of R with the induced order. Okay? So this is another example of valuation, and this tells you already that in dimension 2 you have many possibilities. Let me give you another example again. Take a series, sum of ak xk, which is not algebraic over the field k of x. I hope this is clear. It means that there is no polynomial p of x and y with coefficients in k of x, y, such that if I call this z, p of x and z of x is identically 0. There does not exist any polynomial like that. Okay? And there exist many series like that. It's a very nice classical result that if you have, well, take for example, take e to the x, I assume that it starts from 1. Okay? Take e to the x minus 1. That is a series which is not algebraic because e to the x is a transcendental function. And you have zillions of functions like that. Now, let me map my localized polynomial ring to k of t by sending x to t and y to z of t. Okay, this series. I claim that this is evaluation, taking the t-adic order, and here I have the t-adic order. If I take any polynomial, p, in x and y, I substitute t and z of t. And the thing to notice is that this is never identically 0, because my series was algebraically independent. Because it's never algebraically 0, it always has an order in t, and this order in t is evaluation. So geometrically, what have I done? I have in my plane, I have taken a curve like this, y equals z of x, and I take a polynomial, that means a function on the plane, I restrict it to the curve, and I compute its order. And I've made sure that the restriction to the curve cannot be identically 0 by this algebraic independence condition. I was telling you that valuations, you can think of them as measuring how much the functions in your ring, how much they vanish along something. And you see that the something can be pretty varied. It can be a curve like this. In fact, I could have taken any curve, even with singularities, provided it's sufficiently algebraically independent. I could have very well taken here a singular curve, algebraically independent, and then I look at its normalization, and I do a similar thing. But let me show you now, before I go on, this is done in the plane. Now we are dealing with the field of rational functions. I can take the plane and make any kind of birational modification of the plane. I will still have the same field of rational functions. And if I take a point here, and I take a function here, and I lift it, I compose it with the map, and I evaluate its valuation there, I get new valuations down there. So all the list I've shown you is insufficient. You must sort of saturate it with respect to birational maps. Okay? We'll come back to this later. For example, I suppose, who doesn't know about blowing ups? My candidate is writing. Do you know? Do you know about blowing up? Okay, well that's good enough. Sorry? Okay. Well, so suppose again I have the plane. I'm looking at the origin, and then I blow up the origin, and I pick a point on the exceptional divisor. And in that point, I look at all my zoo of valuations. Then I take any polynomial here, I lift it through the blowing up map, and I restrict it here, and I get different valuations. Okay. And the next, suppose I take a polynomial here, p of x and y, and so my blowing up is something like, depending on the chart, something like that. So this gives me x to some power s p prime of x prime and y prime. And this s, you think, okay, it's evaluation, it's true, but it's not a new valuation because it's the same one as we had here. Because s is exactly the order of p at the origin. So this one is not new. But what I can do is associate to p the integer s, and then p prime does not vanish. X prime is no longer in factor. So p prime does not vanish along the exceptional divisor, which is x prime equals 0 in this chart. So I can look at the order along the exceptional divisor of p prime. This has a meaning. And this pair with the lexicographic order is again evaluation, which is not comparable with any of those which I've shown you so far. Okay. So what is the value group? It is Z2 with the Lex order. I first look at the value of S, and then if to compare two functions, I first look at the value of S. If one is greater than the other, then the functions are in that order. And if they are the same, then I look at the value of mu e. So this is an example of what we will soon know as evaluation of rank 2. The value group is no longer Z, but it's Z2 with the lexicographic order. And for those of you who are not completely familiar, you must begin to think, if I may give advice, geometrically. So this is Z2 with 2 coordinates. And the lexicographic order means I first look at this coordinate, okay? And then I decide where it is. So this is Z2 lex. And now, if I want to look at those, so this is a totally ordered group. That's the interest of the lexicographic order. I can compare any 2 points in Z2. It's a totally ordered abelian group. But if I want to look at the positive part consists of all the elements where the first coordinate is 0 and the second coordinate is positive, and then all the elements where the first coordinate is positive. So all the integral points on all those lines. This is the positive part. And you see that this is more complicated than the integers. In particular, it is not a well-ordered semigroup. It has infinite decreasing sequences of elements. So you must keep in mind this picture because it's very useful to understand the more general cases. And finally, let me show you the valuations which are really those which are difficult to deal with, which nobody loves, except me. And it begins like this. Take a sequence of integers. So Si from I equals 1 to infinity. And I assume that Si is at least 2 for I at least 2. Then I'm going to describe a certain semigroup of positive rational numbers. It goes like that. Gamma 1 is 1 over S1. Gamma 2 is gamma 1. No, sorry. S1 gamma 1 plus 1 over S1 S2. Gamma I plus 1 is Si gamma I plus 1 over S1 Si plus 1. Okay, so this, given the SIs, this is a well-defined sequence of positive rational numbers. And you can observe that the denominators grow strictly every time, at each step, so that, for example, gamma I plus 1 cannot belong to the semigroup generated by gamma 1 up to gamma I. This means the semigroup generated by these elements. Okay? So altogether, these gamma i's generate a certain semigroup gamma, which has infinitely many generators and which is contained in the positive part of the rationals. Now I claim that one should think of this as a curve. You can think of it as a curve given parametrically by ui equals t to the gamma I. And this curve lives in an infinite dimensional space. That's the way it is. But still, it's like that. And if I look at so this means I can take any field, and I take the semigroup algebra. Does everybody know what the semigroup algebra is? Semigroup algebra, when you are given a semigroup and a ring, you look at all the combinations, all the formal combinations, like that. I mean, I ring a field, it's not really important. So, and this is, you can multiply two such things in general. You can multiply them, well, in general, if there are infinitely many generators, you may have a problem. But we won't meet that problem for reasons which I will explain later. But if it's a finitely generated semigroup, not like here, but in this case, the semigroup is well ordered. It's very easy to check. There is no infinite decreasing sequences of elements in it. And therefore, this is really an algebra. You can multiply two. Well, sorry, I've been too fast. I've been much too fast, sorry. These are polynomials, so of course you can multiply them. But in a short while, I will take infinite sums like that. And then the problem of multiplication arises. But in my case, there is no problem because I take finite sums. In this case, this is finite sum, so it's an algebra without. And it's a theorem due to Pilton that whenever you have a semigroup algebra like that, it's cruel. It may not be Noetherian. Like here, it's not Noetherian because the semigroup is not finitely generated, but nevertheless, it has a certain cruel dimension, which is the rational rank of the group generated by the semigroup. So this gives me the opportunity to define the rational rank of a group, of an abelian group. It is thus dimension over Q of phi tensored with Q over Z. I have an abelian group. It's a Z module. I can tensor it with Q. Q is flat over Z. And this a priori may be finite or infinite, but for some reasons which will appear in algebraic geometry, we will meet only the case where this is finite. And whenever you have a semigroup such that it generates a group of finite rational rank, then the dimension of the semigroup algebra is the rational rank of the group. So in this case, the group it generates is a subgroup of the rationals. So it is of rational rank 1. And so the cruel dimension of this ring is 1. So you can really think of it as the ring of a curve, even if this curve is a little bit unusual in the sense that there are infinitely many variables and the exponents are rational. But expand your mind. It's just like a curve. Okay? So now what do I do with this curve? Well, what I'm going to do is to show you that from this curve I can build a valuation whose group of values is the group generated by the gamma i's. The group generated by the gamma i's is a complicated group. In fact, if you choose for example, if you choose all the SI, if you choose SI equal to I, then the group I get is the rationals as an additive group. So this is not at all a finitely generated group. It's a pretty large group as an additive group. So let me show you how to make a valuation out of this. This is where you can smell the first whiff of infinite dimensional geometry. We are doing infinite dimensional geometry there. My curve is in an infinite dimensional space. So the first thing to do when you want to deform something is to find equations. How do I find equations for this curve, which is given parametrically like this? Well, the equations have to come from the relations between the generators gamma I, because they're not free. There are relations between them. And in fact, it's a computation which I won't show you. The relations are of this form. That means for every I, we know that gamma I cannot possibly belong to the semigroup generated by gamma I up to gamma I minus 1.
You meant to sum over k equals 1.
Sorry, yes. Thank you, David. So we have seen that gamma I cannot possibly belong to that semigroup, but its multiple belongs to it. That's not very long to check. So this is just writing that this multiple depends on the Lik are in M. So I'm just writing that. These are relations between the generators. And they give me relations between the coordinates of my curve. Because look, T to the Si gamma I is equal to T to the sum Lik gamma k. This means that Ui to the Si is equal to the product of the Uk to the Lik. And these are, it has to be proved, of course, but it is true that these relations generate all the relations between the UIs on my curve. So this is a system of equations which defines my curve in its infinite dimensional space. I have an infinite system of equations which define my curve in an infinite dimensional space. We are doing geometry in infinite dimensions. Now, once I have that, I write them in a different way. And then I perturb them. I told you if you want to deform, I look at this new system of equations. And let me give you an idea. It begins by u2 to the s2 minus u1. I think in this case it's s1, s2 plus 1 minus u3, u3 to the s3 minus u1 to the l3, 1, u2 to the l3, 2 minus u4. And it goes on like that indefinitely. Okay? So this defines, in principle, a new curve. Okay, I start from a curve, I deform the equations, I'm expecting to get a curve. Okay? Wrong. Wrong, because you see that u3 depends polynomially on u1 and u2. u4 depends polynomially on u1, u2, and u3, and therefore on u1 and u2. And it goes on like that. So if I eliminate successively all the u's, I find that the quotient ring, so let me give a name to these equations. Let's say F2, F3, and so on. This is isomorphic to K of U1 and U2. Okay? I have shown you the isomorphism. So I have deformed the curve, and I find a plane. This is the beauty of infinite dimensional geometry. But you can understand it. And in fact, in the last 5 minutes, I'm going to show you that this is not quite as mysterious as it seems. And why does it give a valuation? Well, look at it this way. I have my infinite system of equations, but I could truncate it at some point. From now on, my field is in characteristic 0. What I say is still true in characteristic P, but the proof is much more messy. So in characteristic 0, if I stop at some point, and I just forget the next one, so I keep the equation here and take 0 and forget all the rest. Okay? I have a finite system of equations, and if I eliminate, like I started to do, I find some, suppose I stop at Fi, I find some curve phi of u1 and u2 equals 0. Okay? It turns out that this curve is analytically irreducible, and following the Newton algorithm, you can write a solution as a Puiseux series in u1. So this is written as the u2i, sum of aki, u1 to the b of k, something like that, I. Some exponents, which are rational. Okay? Some Puiseux expansion. Now, again, it turns out that when I increases, all this series, to what this series sum of aki, u1 to the bik of k, they all belong to, let us say, the series with rational exponents, but now because the positive part is not well-ordered, you have to assume that the exponents form a well-ordered set. So you look only at the series whose exponents form a well-ordered set. It turns out that these u2i, when I tends to infinity, they converge to a series u2 infinity in the same ring. I should have put positive here. But now, what happens is that this series, if you look at the exponents, the denominators of the exponents, tend to infinity. Because here the denominators, this is of the form, whatever, C divided by S1 Si. If I stop at step I, all my exponents have denominator S1 to Si. If I go to step I plus 1, then the denominator will be Si up to S times Si plus 1, and so on. So as my series continues, the denominators will grow. So this cannot possibly be a Puiseux series, because in the Puiseux series, the denominators are bounded. So what have I done? I have created a kind of ghost curve, which does not exist in algebraic geometry, because it's not a solution of anything, power series, whatever. But still, it exists as a valuation. Because if I take any polynomial now, P of U1, U2, and in this polynomial, I look at P of U1 and U2 infinity of U1, I substitute. Then I look at the order in U1. This is some element, actually, of the semigroup, which is here. It's well defined, and it gives evaluation. So what have I done from the viewpoint of algebraic geometry? I have this kind of ghost curve, which does not exist in algebraic geometry. But, and why do I get the plane when I eliminate? Because elimination computes algebraic things. So it computes the Zariski closure of this curve. It does not compute the curve. It computes the Zariski closure of the curve, because it doesn't know better. That's all that algebraic geometry knows how to do, compute Zariski closures in this kind of example. So it's not so surprising. I deform a curve, I get a curve, but this curve does not exist in the world of algebraic computations. Only its Zariski closure, which is the plane, of course. So that's why when I deform the curve, I get the plane. And this was my first session of advertisement to say that when you look at valuations, you see things which you do not see in algebraic geometry. And this is the kind of thing. Now, next time, in half an hour, I will continue and explain to you why this kind of thing, we would like to avoid it, of course. But we can't. We can't if we want to prove local uniformization in general. Or if we are thinking about resolution of singularities, we have to take those types of valuations into account. But I just wanted to show you, because I think it's instructive to see how one can... and you remark that I deformed something which was completely algebraic, but living in infinite dimension, to get something which was totally non-algebraic in any sense of the word, but in the plane. So this is the balance that you have to keep. And in fact, the purpose of my lectures is to show you the kind of method that I want to use to produce this, to understand rather this kind of phenomena in general. Without, in fact, because here we don't have to, we are on a non-singular space, the plane. Now we want to understand the same phenomenon when the ambient space has singularities. And it's a little bit more tricky. So thank you for your attention.
Your description of the ghost curve makes me wonder if there's some connection between valuation rings and dynamics.
Yeah, in fact there is. That, and it's precisely the same reason. It started some years ago when Charles Fabre asked me, he had some problem about automorphism of a plane, and iterating automorphism of a plane which kept the, and finding fixed points for the iteration. And I told him, if you stay in the plane, nothing good can be done. But if you go to the space of valuations, it's compact. So there, as soon as you have a little attractivity, you will have fixed points. So that's what he did, and it worked very well. And the reason why we have to look at these valuations is because we want the space of valuations to be compact or quasi-compact. And it's exactly the same reason why now they are doing a lot of dynamics on the spaces of valuations. And they can do it because, essentially, it has this nice property of being quasi-compact. Of course, they have proved much more beautiful things about its structure, especially in dimension 2, that it is a tree, and that on this tree you can really do analysis, you can have a Monge-Ampère operator, you can do lots of things. So they have proved many, many beautiful theorems, but the basic fact is that you need to have a compact space on which to work. And in order to have such a space, in some guise or other, you must have this kind of object in your perspective. If you try to avoid it, you look only at simple valuations, you will always find that there are limits which do not exist, because there are limits of simple valuations.
Okay, so we are going to take a little break, and then we're going to come back for the second part of the lecture. Let's thank Professor Teissier again.